morning and rather afternoon. Okay, so this afternoon we study at rooms 520. So to have all of you clearly understand my lectures, I ask lab engineer Mr. Hill will record my lectures. Okay, so if you don't understand fully, you can watch the video of my lectures at home. So last week we discussed about AC machine fundamentals, and we know every AC machine we have stator winding and rotor winding. So when we apply Faraday's law, we can analyze the induced voltage. Okay, at the stator. And we also get the induced voltage at the rotor. Okay, for example, we have magnetic core and we have the winding. Okay, for example, this one is stator winding. Of course, for three-phase AC machine, we have three windings: winding A, winding B, winding C. Okay, you remember that one winding we have many coils. Okay, and one coil has many turns. Okay. In general, we have n turns. So here, if we have permanent magnet like this one, okay, we have north poles and south poles. Okay, so this one will generate magnetic field. Okay, and then when the magnetic field goes across the winding, they will generate the induced voltage. Okay, so here we have magnetic field. So magnetic field come from rotors. We say VR. So remember that for rotor magnetic field, we have three parameters. This is magnetic densities, this is magnetic intensities, and the last one is magnetic flux. Yeah. They have the same direction. Okay. So if we have rotating magnetic field across the winding, they will generate a voltage. Okay. So we have three kinds of magnetic fields, right? The first one is constant magnetic field. The second one is varying. Magnetic fields. And the last one is rotating magnetic field. Okay. So when we apply a DC current, I mean the IDC. ID. So when we apply IDC current, we can get constant magnetic field. So when we apply single phase, or we say is 1-5. Okay, this is a abbreviation of single phase current. We can guess IAC 1 phase. Okay, you can get the varying magnetic field. And then if we apply 3-phase current, IA, IB, and IC, okay, we can get rotating magnetic field. Okay. So this is general ideas of induced voltage. Okay, we apply Faraday's law. Look. This permanent magnets move upward, downward. Okay, yeah, they can get rotating magnetic field. So for the induced voltage, this is AC. Okay, we say it's EMF. What does it mean? Is EMF. So EMF is electromagnetic force. Sorry, electromotive force. Sorry. Electromotive force. EMF. Okay. Look, a rotating magnetic field can produce a 3-phase set of voltage in the coil of oscillator. Okay. And then last week we also discussed about the induced voltage in a coil on a 2-pole cycle. Of course, we know every machine, the number of poles is even. For example, we have 2, 4, 6, blah blah. Okay. And here we have 2 poles, right? Yeah. So I just pick up. We just pick up a phase to analyze the induced voltage. Okay. Of course, we know for one winding we have many coils, and one coil has many turns. Okay, so for simplicity, we only pick up 1 turn. Okay, so 1 turns we say 1 loop. 1 loop, right? Okay. So every loop we have 4 segments. Look at this one. AB, BC, CD, and BN, right? Okay. So that's the reasons. If we have 1 winding has n turns, that means we have n loops. Is it clear? Yeah. So now we just think of 1 loop. Okay. So here we have 4 segments. Okay. Yeah. A, B, C, D. Yeah. So if we have n loops, of course, yeah, the same to analyze this induced voltage. Okay. So I mentioned before we get a bit of 1 phase. Okay, phase A. Here, it's in phase A. Okay. So here we have a stator. We have stators. Okay. So if we put this lock inside the stator, you know, so you hear this A, AB. This is C. Okay, because current flow this way. Okay. If we consider the surface, if the current flow is the surface, you get cross. If the current flow out of the surface, you get dot. Okay, dot. Right? Okay, I will see it. We are considering the induced voltage at the stator. So we assume that we have rotating rotor magnetic field. Okay. Okay, so we have this one, we have rotor. Rotor. Yeah, rotor. We are considering two poles, right? Two poles. Two poles. So we have rotor magnetic field like this. Okay, this is VR. With a straight R means rotor. Okay, yeah. So if the rotating magnetic field from the rotors goes across the stator winding, they will get the induced voltage. Okay, yeah. So so we have two conditions of rotors. So if the rotor is stationary or is fixed, that means they are not rotating. Yeah. So we can get BE. We can get the BR is BM cosine alpha. Cosine alpha. So at the beginning, if the rotor position is in the same line with the stator lock, okay, you get alpha A0. Okay, so if the position of the rotors is shifted a little bit, for example, here is rotor, yeah, here rotor, yeah, we can get alphas, different ones. Okay. So in general, we have this one. Now, if the rotor is rotating, right? Yeah. So if the rotor is rotating, we have BR is BM cosine omega t plus alpha. So why we have omega t? Omega t means theta. What is theta? Theta is the angle of the rotor rotation. Okay? Yeah. So if we go back to the physics theory, we have theta is what? We have omega A derivative of theta with respect to times. Okay? Yeah. So if the interval of theta and the interval of times are very small, we can get omega is approximately equal to theta divided by okay, or delta theta over delta. Okay, so delta theta is omega. Okay, so theta is very small. Delta theta is very small. Okay, so we have delta theta is approximately equal to theta. So we can get theta is omega. Yeah. Okay. Of course, for the operation of the machines, the rotors will rotate, right? Oh, sorry, this one is minus. This one is minus. Why? Because they already have this phase angle angle before. So if the rotor rotates, you need to minus. This is phase shift. This is phase shift. Okay. And here we have the waveform of magnetic field, sorry, magnetic densities. Yeah. Look, if n is zero, we can get maximum magnetic density, right? Because we are considering cosine. And the rotor rotates with the angle frequencies of omega. Omega, or sometimes we say omega m. What does this mean? M means motor. Okay. So now we apply right hand rule, right? To determine the induced voltage E. E means induced voltage or EMF. So E is vector product, right? V cross B is vector product. And then dot product with L. What does this mean, L? L is the length of conductors in the magnetic field. So actually here we have 4 segments, but we don't care about this segment and this segment. Why? Because BC and DIE are in parallel with the rotor magnetic field direction. Okay? Yes. So we don't have voltage. So we just focus on AB and C. Okay? So this is L. L. Yeah. So sometimes we say L is the length of conductors, or L is the length of rotor shaft. Yeah. Okay. Any questions? Yeah. So we apply this general formula into 4 segments, right? Yeah. We have 4 segments. Segment A. Actually, we use the BI. Yeah, I mentioned before, right? Yeah. So if we follow the direction of the current, okay, and we go back to the theory of electric circuit. So if we have a voltage source and we have resistive load, right? So the current is always free out from the positive polarity. Okay? So this is the law. So the current is always coming in to the positive polarities. Okay? So now, if we would like to determine the polarities of the voltage, and if we follow the current, right? If this is positive, this is negative. Okay? So this one is positive, negative, positive, negative. Okay, so that is the reason here we have positive polarity here, negative polarity here, because we apply this theory. Okay, so here for segment AB we have the induced voltage VA. Okay, from positive. Yeah, of course. So if we have the closed circuits, this is closed circuit, right? This is closed circuit. So for example, this is point A, this is point B. So if you get the voltage here is VAB. Okay? So VAB is what? VAB is minus VB. Okay? For example, here if we connect this one is this is the round. Yeah. So we have VAB is VA minus 0 because it is 0, 1, we can get that. Okay? Yeah. This was just fundamental of electric circuit. Now come back to EVA. So for EVA, we have V cross B totally dot L dot mean dot product. Okay? And here, where is VA? Here. Okay. So this is the direction of velocity. This one is not the magnetic field direction because here, I trot here. Okay, upward direction is VR. Okay, so now we temporarily since this is going down. Yeah. So we have formula here. Okay. Continue. EVA is V B L. Why? Because the segment AB is perpendicular to magnetic field direction. Okay? Yeah. So sine 90 degrees is actually here V cross V times L. This is magnitude. So we can get magnitude, right? So magnitude of V cross V is V sine theta, sine of phase angle between V and B times. That's right? Yeah, and AB is perpendicular to magnetic field density. So that means it is 90 degrees. Yeah, so since sine 90 degrees is 1, so you get VBL. Here. Okay, so continue. Yeah. So we can get VBL. So what's EB? What is B? So B is B means BR. So B is BM, right? BM. Both sides. Omega is look minus alpha times. Problem here. And we have minus here, right? We have minus. And we have phase angle. Look, if we consider the rotor's position like this, and phase 0 degree, now we rotate. Look, now the direction of B is going down. Okay, so we have minus how many? 180 degrees. Is it clear? So if B is good enough, you get positive. So if BR is going down, you get negative. Look, this one is opposite to this one. Okay, so that is the reasons we have minus here. Okay. Is it clear? How are you? Good. But any questions? Yeah, we can modify some minus here, but we shouldn't do that because we apply the general formula here. You know, minus n for alpha is the phase shift of the rotor position. Okay? Yeah. Now, segment. Segment BC. I mentioned before, right? Segment BCE in parallel with the magnetic direction. That mean the phase angle between V. No, I mean with ACB is 0 because segment CB in parallel with rotor magnetic direction. Okay? Yeah. So continue. We have segment DC. Remember that you need to consider correctly the polarities of the voltage. You know, if here you say ECD, very different. You know, EDC is different ECD, right? Because we have the reversed polarity. Okay. Yeah. So now we have EDC. So EDC is what? Here, look. EDC. You know? Yeah. So we can get what? We can get V BM cosine omega t minus alpha times L. Right? And if B is going up, okay, so alpha is what? Alpha is 0. So here, V is not equal. V is not equal. Right? And we don't have minus here because we assume that if BI is going down, you get minus. So BI is going up, you get positive. Okay? So here, positive. Then EDA is 0. EDA is 0. Okay? So then we combine, you know, AB, BC, CD are connected in series. Okay? So the total voltage is the sum of individual voltage, right? So we have E total, right? E total. With E total, all we say is induced. E total. Mean is E induced in this voltage. Yeah. So that's is E BA plus E DC. Here. That means you get formula 1 plus formula 2. Okay. And after some modification, you can get here. You can get 2RL BM omega M cosine omega M T.